This is not a Game Boy. This is a Game Boy. This is a computer called the Thumbie, the latest programmable machine from the company Tiny Circuits. I was lucky enough to be one of the first 50 to grab one when it first launched on Kickstarter, and it arrived a few days ago in the mail. But again, this is neither a Game Boy or a Game Boy emulator. Or is it? Because the Thumbie is easily programmable, and since its Raspberry Pi 2040 processor and 2 megabytes of memory make it a powerhouse compared to the original Game Boy system, it should be able to emulate its functions easily, right? Yes and no. Theoretically, one would be able to write an emulator that would fit onto the Thumbie system and play Game Boy games, but it is unlikely that anyone will ever do that, and we'll see why later on. There are, however, many Game Boy emulators out there already, including those written in Python, the language that the Thumbie is programmable in. But the best available Python Game Boy emulators require a large percentage of a gigabyte's worth of libraries to function, something that the Thumbie just doesn't have the space for. But there is still one solution. Use another machine to run the actual emulator in the background and then send that data to the Thumbie. This can be done quickly as well, because just like my old BBC Microbit, the Thumbie communicates as a serial device. This means that we can communicate with this device by sending data to it, and it can send data back as well. Normally, programs for the Thumbie are written using the help of the IDE that Tiny Circuits have created for communicating with the Thumbie. But essentially, all it does is open a serial port with the Thumbie and then transmit the data and files back and forth. They do this in the browser with JavaScript. But we can do the same thing outside of this web IDE in Python by using the PySerial library. Once a port is opened, we can send commands to the Thumbie for it to execute just as if we were executing a script line by line, and then the Thumbie sends data back to us to let us know that the commands were executed properly. But before we go any further, let's understand why the Thumbie will never be able to play Game Boy games on a 1-to-1 scale. The simplest explanation being that it isn't a 1-to-1 recreation of a Game Boy, nor is it meant to be. The Game Boy had a 160 by 144 display, but the Thumbie's is only 72 by 40, meaning that not only is it smaller, but the wrong XY ratio as well. So any game will appear smaller and squished vertically. The original Game Boy also used grayscale graphics, meaning that even though there is no color, there are multiple shades of gray that every game implements. While you might hope that the Thumbie outperforms here, it doesn't. There are only 2 pixel values its screen can have, black or white, so not only are images from the Game Boy going to be shrunk, they will need to be recolored as well. I found that the best solution was to apply threshold to the Game Boy's image first, turning the lighter shades white and the darker black, followed by a nearest neighbor scaling down to get crisp edges. Honestly, sometimes it doesn't look half bad, but anything like text is completely unreadable at this point. As a side note here, I can't just tell my Thumbie to draw this image onto the screen. It first has to be converted into a byte array. Each byte in this array controls 8 vertical pixels, with each bit in the byte controlling a single pixel, flipped on for white, off for black. A completely black screen being 360 bytes all equaling 0, and a white screen being 360 bytes equaling 255. But once a function is written to process images to this array of bytes automatically, I never have to think about it again. For this project, I chose to use the PyBoy emulator, written by these lads from the University of Copenhagen, because it has some great scripting features, including easily capturing the emulation window. After the screen is captured, the data is thrown through the algorithm that was talked about before, giving the byte array that is then sent to the Thumbie to produce 1 frame of the game. Do this frequently enough, and still pixels give the illusion of movement and life. Now that the game can be seen, the next natural step is interacting with it. After all, the Thumbie has these buttons on it for a reason. Thankfully, in order to read which buttons are pressed, all we have to do is say, please, or rather, print. All print commands are given back across the serial port, so I can ask which buttons are being pressed and then send these button presses back to the emulator to process. But you may have seen that there are 8 buttons on the Game Boy, but these little stubs here on the Thumbie aren't buttons at all, leaving 6 buttons to process 8 possible inputs. My solution was to press A and B at the same time to signal start, and up and down at the same time to signal select. While I'm not sure if this will impact gameplay in any way, my code is available for you to edit if you feel it does. and if you think of a better way to process these two buttons, feel free to do so. Essentially, now we have a working Game Boy on the Thumby, and we're able to run any game that we want to and play it more or less normally. But one issue with the Python code here is that there is no way to run both the emulator and the Thumby I/O asynchronously. Ideally, the emulator would keep running in a different thread as the screen data is sent to the Thumby and the button data comes back. But unfortunately, using this vanilla programming language, it's not possible. So because of this, the emulator will process about 6 frames for every one that gets sent to the Thumby. This is the balance that I found made the games run in about real time, while accounting for the data transferring delays without impacting the overall experience too much. But feel free to play with these numbers in the code for yourself. There are non-vanilla solutions to this problem of synchrony, such as using Jython or IronPython, but I wasn't sure that was the way I wanted to go. Instead, I just rewrote the whole program in a completely different programming language that was still able to open a serial connection. That's right, we're using my old pal JavaScript. With a little borrowing of the serial code from the Thumby IDE page, I was able to recreate the previous Python program into a very asynchronous web app, meaning that yes, the emulator does continue running as the Thumby communicates with the machine. There are a few minor changes to this version of the program though. First, the JavaScript Game Boy emulator used here, Gameboy.js, may occasionally have a few sprite issues. The web version is also susceptible to once in a while dropping a return call from the Thumby, resulting in what might be about a 1-second delay. But after a quick patch, I couldn't even notice the issue anymore, partially because, as you may have seen before, this doesn't capture and send every single frame to the Thumby. Just as with a Python version, close enough is good enough. If you have your own Thumby and want to run real Game Boy games on it, you can download the Python version or go to natin.tokyo/gameboy. Plug in your Thumby, boot it up, point it to your Game Boy or Game Boy Color file, connect, and start playing. If you'd like to see more interesting things like this, consider subscribing, and feel free to reach out with any questions down in the comments. And until next time, thanks for watching.